In this video, we're going to do some extra examples of definite integrals, so computing them using the fundamental theorem of calculus, or sometimes we denote it FTC, and then also talking about how this relates to the area under the curve. So let's start with this first one here. So we have the definite integral from -1 to 2, and our integrand function is 3x squared minus 4x plus 2. Okay, so the first thing we want to use the fundamental theorem of calculus here. We don't care about the area, so it's possible this could be a negative number. That would be fine. So what we want to do is compute the an antiderivative. So there's actually two ways to do this. So we could break it up and do each part separately if you want, or we can find an antiderivative of this and then use that. Okay, so either way is fine. I'm just going to, on the side here, talk about the indefinite integral. Okay, so we've done some like this before, so you can do each part separately. Okay, so the first one is going to be x cubed. The second one is 2x squared. And then I have a plus 2x, and then I would have my plus constant, so I can use this as my antiderivative up above. Okay, so what this is going to be is that antiderivative, so x cubed minus 2x squared plus 2x evaluated from -1 to 2. Okay, so that means we want to take this whole thing and plug in 2 everywhere, so 2 cubed minus 2 times 2 squared plus 2 times 2, and then subtract again the whole thing with -1 plugged in. So -1 cubed minus 2 times -1 squared plus 2 times -1. So we could compute these separately, or you can just expand it all out. Okay, this is going to be 8 minus 8 plus 4 minus -1 minus 2 minus 2. So I get 4 and then minus -5. So that's going to be 4 plus 5. So this definite integral actually equals 9. Okay, now again, like I said, you could do each of these definite integrals separately. So you would do x cubed evaluated from 2 to -1 to 2. And then you can do them each and add them up. You'll get the same answer. Okay, so let's try another one. So here, you might know the antiderivative here. I'm not sure. Or you might want to use substitution. So I'm going to use substitution just for practice. So I don't want the dot. So let's say I let u be the inside of the sign, so 2 theta. That means that du is equal to 2, the derivative of that, times d theta. And I have a d theta, so I'm going to move the 2 over. So 1/2 du is equal to d theta. Okay, and then if I go back, I also here, because I have a definite integral, I want to change the bounds. Okay, so when theta equals 0, the bottom bound, u is going to be 2 times 0, so still 0. Okay, but when theta equals pi by 2, u is going to be 2 times pi by 2, which is just pi. Okay, so I also want to change the bounds. So when I do this, okay, so the 2 theta, that's my u. Okay, d theta I know is 1/2 du. And then this bottom bound is still 0. And then the top bound is now going to be pi. Okay, so that's how everything's going to change. So this is going to be from 0 to pi. Now instead of sine of 2 theta, it's going to be sine of u times 1/2 du. So bringing the 1/2 out, because it's a constant, this is going to be the integral of, from 0 to pi of sine u du. So now I want to think, okay, what function has derivative sine u? Well, that's going to be negative cosine u, Okay, and I'm going to evaluate from 0 to pi. Now I don't have to go back to thetas because these are the bounds for u. Okay, so that means that I can just use the fundamental theorem right away. So this is going to be negative 1/2 cosine of pi minus negative 1/2 cosine of 0. Okay, cosine of pi is negative 1. This is going to be a plus 1/2, and cosine of 0 is 1. So I end up getting 1/2 plus 1/2. So my definite integral here is equal to 1. Okay, let's try another one. So again, a definite integral here, I definitely want to use substitution because I don't know what the antiderivative here is. Up above, I should say, so you might have known, okay, so maybe you knew that the antiderivative or unantiderivative of sine 2 theta is negative 1/2 cos of 2 theta plus a constant. Okay, so you might have known that, and then you could have used this right away, and you would have got the same answer. You wouldn't need substitution necessarily. Okay, for this one, I think we probably do need substitution. So I'm going to let my u be the exponent of the exponential function. Okay, so that's x plus 1 to the 1/2. So that means that du is going to be the derivative of that. So 1/2 x plus 1 to the negative 1/2 times dx, times the derivative of the inside, which is 1. Okay, now if I rewrite this, so it goes from 0 to 8, it's e to the square root x plus 1 times 1 over square root of x plus 1 times dx. So I actually see that this looks a lot like what I have because x plus 1 to the negative 1/2 is 1 over the square root of x plus 1. So here I see that I have that. So I'm going to move the 1/2 to the other side and say that I have 2 du is going to be equal to 1 over square root of x plus 1 dx. Okay, now I also want to change the bounds. So I go from 0 to 8. So when x is 0, u is going to be the square root of 0 plus 1. So that's the square root of 1, or 1. And when x is 8, u is going to be the square root of 8 plus 1, so the square root of 9, which is 3. Okay, so I can change all of that. So I guess let's use our colors here. So this part is my u, so it's going to be e to the u. All of this is equal to 2 du. And then my upper bound, the 8, that's going to be the 3. And the 0 is going to be replaced with a 1. Okay, so when I switch to u's, this is going to be for the definite integral from 1 to 3, e to the u times 2 du. Okay, so I can pull the 2 out because it's a constant. And now I know that e to the u is its own derivative and antiderivative. So this is 2 e to the u evaluated from 1 to 3. So it's going to be 2 e to the 3 minus 2 e to the 1. Okay, so if I compute that, I mean, you don't have to. You get something, it's approximate 34.735 about. Okay, you could leave it as either. I actually prefer with the e's, but if you want to change it to decimal, that's what the decimal would be. So that was another example using substitution on a definite integral. Okay, another one. This one is a little bit harder, it turns out. So let's let my u be the inside of the square root, so 2x plus 1, So that means that du is 2 times dx, so the derivative of 2x plus 1. And I only have dx there, so that means that 1/2 du is going to be equal to dx. And I know I also want to change the bounds, so x equals 0 means that u is 2 times 0 plus 1, so 1. And x equals 4 means that u is 2 times 4 plus 1, so that's going to be 8 plus 1, so 9. And now let's try to start replacing. Okay, so the 0, that becomes a 1. Okay, the 4 is going to go to a 9. We know that this part in here, that's my u. The dx is 1/2 du. But what about this part? Okay, so I still have an x left over that I don't really know what to do with. Okay, and that's where this equation can come in as well. So if I solve for x, 2x is going to be u minus 1, which means that x is u minus 1 over 2. I can plug that in for x. Okay, so that's my x value. So my integral is going to become the definite integral from 1 to 9 of u minus 1 over 2 times root of u times 1/2 du. Okay, now this looks worse. It doesn't look better. But it is in fact better. Okay, the reason why it's better is because here, because of the square root, I cannot bring the x through inside those brackets. Okay, but here, because the thing that has the minus is exponent 1, I can actually bring the square root through. Okay, so that's going to make things easier to work with. But first I'm just going to rewrite this. So u minus 1 over 2 is like 1/2 times u minus 1. And square root I can think of as u to the 1/2. Okay, so these 1/2 can go together and come out as a 1 over 4. And then I can bring this through. Okay, so that's going to be u to the 3 over 2 minus u to the 1/2 du. Okay, and now I know how to integrate this. Okay, so u to the 3/2 has to come, we add 1 to the exponent, which is not going to be, so it's going to be 5 over 2. So that means the constant out front should be 2/5. And then when I have a 1/2, I'm going to add 1, so I should have a 3 over 2, which means the constant out front is going to be a 2/3. And then I want to evaluate that from 1 to 9. Remember that I do not need to go back to x because these are the bounds for u. Okay, so I'm going to simplify a little bit before I plug everything in. So if I put the 1/4 in, this is going to be 1 over 10 u to the 5 over 2 minus 1 over 6 u to the 3 over 2. Just to make things a bit easier, I want to evaluate that from 1 to 9. Okay, so that's going to be everything with 9 plugged in. So 9 to the 5/2 minus 1/6, 9 to the 3/2 minus everything with 1 plugged in. Okay, so then 9 to the 5 over 2, so 9 to the 1 over 2 is 3, and 3 to the 5 is 243. Okay, again, square root of 9 is 3, and 3 cubed is 27. And then I'm going to subtract over here, this is going to be minus 1 over 10, and then plus 1 over 6. When the negative gets expanded through. Okay, so now I just want to put these together. So this is going to be 242 over 10 minus 26 over 6. Okay, so if we compute that, we get 298 over 15, which is approximately 19.867. Okay, so that's what our definite integral would equal here. So that was a tough one just because we have this extra step of an extra x value here that we can use the u substitution to get rid of. Okay, so now let's move into area. So what if I want the area between the graph of y equals 1 minus x squared, the x-axis, and between x equals 1 and 3? So here, I probably don't need a sketch, okay, but here we can sketch this one because we should know maybe the shape is a parabola that opens down and that intersects, that's been shifted up by 1. Okay, so our shape looks like that. Okay, now where it crosses, I should have made this a bit more rounded, but you know what I mean. So where it crosses, this is actually, we know this is at 1 and minus 1 because you can factor. So if we want the area between this and from 1 to 3, I should have drawn this a bit higher, I guess. Okay. What we're looking for is this area here. And because we're talking about area, we want it to be a positive number. Okay. Now, if you didn't know the graph, okay, so without the graph, what you'd want to do is find where your function equals 0. So that I could factor as a difference of squares. Sorry. 1 plus x. So I get x equals 1 and negative 1. Okay, negative 1's not in our interval, so we don't really care about that one. And 1 is actually the end of our interval. So then we just have to check a number between 1 and 3 and see if our function is positive or negative. So let's say we check 2. 1 minus 2 squared is negative 3, so I'm below. That's enough, okay? So we know that it's below. So that means that the area is going to be the absolute value from 1 to 3 of our function. The absolute value of the definite integral. Okay, so we can compute this. So if we find an antiderivative of 1 minus x squared, that's going to be x minus 1/3 x cubed. And I want to evaluate it from 1 to 3. Okay, so then I plug in 3 everywhere. So that's 3 minus 1/3 3 cubed. Minus 1 minus 1/3 times 1 cubed. Oops. Okay, so that's going to be 3 minus 9. So that's going to be minus 6 minus 1 minus 1/3 is 2/3. So I get the absolute value of negative 20 over 3. So the area is going to be positive 20 over 3. Okay, which is approximately 6.667. Okay, so that's the area in this situation here. Okay, let's try another one. So here we might not know the graph. Okay, so I'm going to do this one without the graph. I want to know where is negative x over x plus 2 positive or negative. Okay, so that means I want to find its sort of critical number. So I want to know, where does it equal 0? Okay, so that's negative x over x plus 2 equals 0. That's going to be when the top is 0. So that's when x is 0. Okay, and I also should think about where does it not exist, because it could switch from positive to negative there. That's going to be when x plus 2 is 0, when x equals negative 2. Okay, negative 2 is not in our interval, okay, because we're going from negative 1 to 3, so we don't have to worry about that one. Now we could check, okay, so negative 1 to 3, and we know that it could switch at 0. So let's find out if it does. So you check a point, so maybe I check negative 1/2. So if I put in negative 1/2, I'm going to have a positive number on the top and a positive number on the bottom. So I'm going to be positive in that interval. If I check, say, 1, I'm going to have a negative number on the top, positive number on the bottom. I'm going to be negative in that interval. Okay, so that means that the area is going to be the definite integral from negative 1 to 0 of negative x over x plus 2 dx, okay, plus the absolute value of 0 to 3 negative x over x plus 2 dx. I guess we could solve this. I didn't intend for it to be this difficult though, but we'd need a substitution, and it's a tough one. Okay, so u is x plus 2, du is dx. So I'm also going to need the x thing, so x is going to be u minus 2. And then let's just not, I'm going to do the indefinite integral here. So it's going to be 1 over u times u minus 2 and a negative, right? Negative and a du. Okay, so if I compute that, I'm going to have to expand this in. So it's going to be 2 u to the minus 1 minus 1 du. So that's going to be 2 ln u minus u plus c. And then I can plug in my x's. So this is 2 ln of x plus 2 minus x plus 2 plus c. Okay, so this would be what I need to use for my function. It's a bit complicated, but if we wanted to finish, okay, it's going to be 2 ln of x plus 2 minus x minus 2 evaluated from negative 1 to 0, and then the same thing but in absolute values. So in fact, I'm going to need absolute values here because I entered this wrong. Oh no, u is x plus 2. Okay, no, it is fine. Okay, and then this needs to be, from 0 to 3 in absolute values. So if I plug in 0, I get 2 ln 2 minus 2. Minus, if I plug in negative 1, I get 2 ln 1 plus 1 minus 2 is minus 1. Okay, now here if I plug in 3, I get 2 ln 5 minus 5. and then 0 is 2 ln 2 minus 2 in absolute values, and then you'd have to compute all of this. Okay, so this is approximately actually, I'm going to do this whole thing here. So this whole part, because ln of 1 is 0, I just have to add 1 to it. So this part should be 0.3863, and then I want to add 2 ln 5 minus 5 minus 2 ln 2 minus 2. So inside the absolute value, I have negative 1.1674. And obviously, I'm going to absolute value that. So it's going to be 0.3863 plus 1.1674. So my final area is going to be 1.5537. Okay, now don't let that freak you out. I made the function too difficult. I was just trying to get something that crossed, and I wasn't thinking about the antiderivative. So you wouldn't see anything quite this complicated on the exam for this part. It should be a more easy function to work with. But you can do this one still, so there it is. But again, don't let it stress you out.